an honor and a pleasure to be here in the birthplace of my grandparents, and a place in this auditorium that I've been to several times before and have happy memories. My time is limited, so I'd better get on with it. There's a lot to say about axions. Let me first tell you what axions are and why we believe they are a very serious frontier of research in physics. The motivation for axions is a series of questions asking why. Few aspects of experience are as striking as the asymmetry between past and future. We remember the past, we only make guesses about the future. We can hope to change the future, we certainly can't hope to change the past, and so forth. If you mix up the cream in a coffee, it's hard to unmix. In general, if you run a movie of everyday life backwards, it does not look like everyday life. So here's an example. If you saw that happening, you'd be very surprised. Even though that movie run backwards, if you examined the microscopic motion of all the particles involved, would be obeying the laws of physics. It's just a very unlikely initial condition with dust on the ground, gathering up momentum, and then making a coherent motion into making a building, and then recombining into atoms, which, when you run the movie forward, powered the explosion. So everyday life doesn't respect any kind of symmetry between past and future or reversing the arrow of time. And yet, time reversal symmetry was a notable property of the fundamental laws of physics for several centuries, starting with Newtonian mechanics, which is based on relating accelerations to positions, and accelerations involve the second derivative of time, so you can change t to minus t. But continuing also through general relativity and quantum mechanics in both its classical and quantum versions. And of course, the Schrödinger equation itself. Why? Why should it be true that this funny feature of the microscopic laws occurs, which is not only not necessary for a description of our experience, but seems to be, it makes problems. And people address those kinds of problems when they worry about the foundations of statistical mechanics. Now, as long as T, time reversal symmetry, appeared to be an exact fundamental feature of physical laws, it was unclear that asking why would be a fruitful question. Those of you who've dealt with small children who keep asking why are familiar with this problem. They can keep asking why until at the end you get exhausted. Say, why is the sky blue? Well, there's the sunlight is scattered by atoms and gets bent around and comes to us. And most of the best scattering is blue and blah, blah, blah. Why? Well, the atoms have electrons and the electrons respond to the electromagnetic fields. Why? Well, there are these quarks and gluons that make nuclei and atoms. Why? Well, there are these strings. And, you can keep asking why until at some point you just have to say, that's the way it is. And at some point, asking why reaches an end. And that might have been the case for time reversal symmetry. It's an elegant principle to state, might have been very fundamental. It would be an attractive final answer. But in 1964, Cronin, Fitch, together with Christensen and Turley, discovered a subtle effect in the decay of K mesons that slightly violates T symmetry. That implies that T symmetry is not rock bottom. So that answer, that's just the way it is, won't work anymore. It's not even quite true, it's just very nearly so. So why? Why is it almost true, but not quite? And a profound result of 20th and early 21st century physics is that we've almost nailed it. We've almost given a good answer to that question. That is that the basic sacred, meaning well-established, nothing is sacred in principle but in physics, but sacred principles of modern physics, that is relativity plus quantum mechanics plus local symmetry or gauge invariance, are very powerful. They constrain the form of fundamental laws in very strict ways. And when you apply these basic principles to the ingredients of matter that we know exist within the so-called standard model, you find that there are exactly two possible kinds of interactions that would violate the symmetry under time reversal. Two and only two possible interactions. One of them involves weak mixing angles and subtle phases within the quark mixing matrix. I won't go into the technicalities. And that beautifully explains what Cronin and Fitch originally discovered and a lot more. Now there's a whole field of particle physics dealing with heavy meson decays and tests of time reversal, including many non-trivial examples of time reversal symmetry in decays of heavy particles. The other interaction is a more subtle one. It is something that appears only when you analyze the standard model, and particularly quantum chromodynamics, non-perturbatively. I'll say a few more words about it as we go along. But the crucial thing for the motivation is that it doesn't happen. So we thought we had this nice explanation where the almost but not quite validity of time reversal symmetry could be ascribed as an could be ascribed to being an indirect consequence of more sacred principles that if they failed, we'd have a lot of unlearning to do. We can put very big constraints on the possible strength of this interaction in nature. It's called the theta term in QCD. And if it did occur with a non-trivial strength, we would observe electric dipole moments of nuclei which are far larger than experiments allow. In the natural units, where the theta parameter would be expected to be of order unity, it's measured to be less than 10 to the minus 10. So that definitely needs explanation. And we have a question, why now at a deeper level? Over the past 40 years, there have been several attempts to explain why, but only one has stood the test of time. That's a little joke, test of time. Thank you. We promote the unwanted term, the unwanted interaction, which appears within the standard model as it comes, as simply a number. We promote it into a dynamical entity, a field. A dynamical entity can change with time, and so it could evolve to zero. in the right framework. That new field, according to general principles of quantum mechanics and relativity, relativistic quantum field theory, is associated with creating and destroying quanta, a new kind of particle, which in this case is called the axion. I actually named it the axion in tribute, in homage, to a laundry detergent. People often don't believe this story, but it's quite true, and here's the evidence. When I was a teenager, I went shopping with my mother to a grocery store, and I saw this product on the shelf, and I said, gosh, that really sounds like it should be a particle. It's a nice Greek name, it's short, it's got eon, like, or on, like proton, neutron. And I said, then and there, I wasn't sure even that, when I was even going to be a physicist at that point, but I said then and there that if I ever got the chance to name a particle, I would try to name it Axion. And a few years later, I got to do that. This particle cleans up a problem in QCD, and it involves an axial current, so it was very natural to call it Axion. The God had spoken. The stars were aligned for this name. What are the properties of this particle? Well, because they're so closely tied to symmetry and its breaking, we can say a lot about the properties of axions. For most practical purposes, I mean, practical has a very special meaning here, meaning for most observable purposes, we arrive at a one-parameter theory. The parameter is usually called F, either capital F or small f, and it has the dimensions of mass in units where h bar and c are taken to be 1. It is associated with the mass scale at which the potential t-violating effects first arise. We have fields evolving, and the amount of t-violation is a function of time in the early universe, a function of temperature, and it's only at a certain point that they start to become significant. Or technically, this is the point at which the deep symmetry that underlies the theory that makes theta, that makes the axion want to cancel time reversal violation, the so-called Peche-Quinn symmetry, when that symmetry is spontaneously broken. Okay. As I said, because of the tight constraints of the sacred principles, and because we're introducing a particle to solve a very, very specific problem through symmetry, its properties are highly constrained. We have just a one-parameter theory. We can write down everything we need to know about this particle in a few lines. So it's a scalar field. It's the quanta of a scalar field, and it has a mass. The mass is given in terms of this parameter f, and involves the scale of QCD. So lambda QCD is about 100 MeV. And then the couplings are to things of the form E dot B, either involving colored gluons or the electromagnetic field. Plus, there are couplings to the different quarks and leptons, all of which are proportional to the masses of the corresponding particles. And there are model-dependent coefficients called C and D here, which depend slightly on details of the model, but they're of order unity. So basically, all the couplings are inversely proportional to this mass scale F, as is the mass. Those are the important qualitative lessons. And the most important qualitative lesson is that we have a very specific class of target theories with one essential parameter. The electromagnetic part the coupling of axions to electromagnetism is especially elegant and central to several search strategies. So I'd like to say a few more words about that. It's also notable that it arises with emergent axions, that is, variables, fields which are describing emergent collective degrees of freedom inside materials, as a description of how these collective degrees of freedom interact with the electromagnetic field. So these equations are sufficiently simple and canonical, connected to a simple canonical Lagrangian, that they appear in perhaps unexpected places. In fact, they give the effective theory of the topological insulators, which have been of tremendous interest in recent years. That's all I'll say about that. So here are the equations. The essential thing is that you have a coupling between the axion field and electromagnetism. There's a parameter kappa, which is very, very different in the cases of the emergent axions or the fundamental axions, but same equations. Other than that, and of course the meaning of the symbol A is different, but same equations. And these are the equations that you derive from that Lagrangian, including simply a scalar field, massive scalar field, otherwise free, that's A, and the Maxwell electrodynamics. This has many remarkable consequences, despite its simplicity. One that you can see is that if you have a magnetic field present, then a gradient in the axion field acts like a source of electric charge. So divergence of the electric field contains a piece which is generated by the presence of a magnetic field and gradients in the axion field. If you have a time-dependent axion field and a background magnetic field, then that acts like a current. And several experiments to search for axions are based on looking at that effect. Also, very important in the condensed matter context, if you have a background electric field and a gradient in the axion, it induces Hall currents on the surface of the material. So you have a kind of Hall effect, a current which is perpendicular to the electric field. So these are the things I mentioned. In the presence of a background magnetic field, the axion field mixes with the photon and pumps electromagnetic excitations. Axions also, through those couplings to quarks and leptons, induce electric dipole moments in nuclei and possibly electrons. So fields that vary in time and space, axion fields that vary in time and space, will induce electric dipole moments in those particles which vary in time. This is another effect that's used to search for the presence of axions in the universe, as we'll see. I remind you that searches for electric dipole moments can be very sensitive. In fact, that's what drove this theory in the first place, that the electric dipole moment of the neutron is 10 orders of magnitude or more less than it naturally should be. So, a stunning consequence of this circle of ideas that emerged from fundamental physics is an important new ingredient in the evolution and content of the universe. The axions are produced, it turns out, if the theory is correct, abundantly in the early universe and hang around, and they're still around us everywhere today. So the axion field is established when the Peccei-Quinn symmetry breaks. I won't have time to enter into details here, but you have a spontaneous symmetry breaking where a complex scalar field gets a vacuum expectation value, and the phase of that field is basically the axion. Or more precisely, the phase is the axion over this fundamental scale f. So this is the mathematical origin of that parameter f. So at the transition, when this phase transition occurs, there's very little dependence of the energy on the value of theta. And this happens in the very early universe when things are hot. So there's lots and lots of radiation and other things contributing to the density of the universe. The contribution from this theta not being at its minimum value at 0 is relatively small. The underlying interactions, technically the underlying instantons are very suppressed, so it's even smaller. However, as the universe evolves, those other forms of radiation dilute, and the time reversal violating interactions associated with a non-zero value of theta become more significant. And so the energy associated with that axion field, if it's not at theta equals 0, starts to become very significant. It becomes comparable to other sources of mass and energy in the universe. And then it starts to settle down and radiate because there's pressure on it from other things, from the fact that now it's significant. The forces can move it, and it eventually settles down. But as it does so, it radiates its content in the form of, or it's a scalar field that's oscillating back and forth. And you can also think of it as a material condensate of the particles the field represents. This is, if you like, a Bose-Einstein condensate, which is just for a massive scalar, a classical field. And one can calculate the stored energy density. It turns out to be proportional to that parameter f and to the square of the sine of the deviation from 0. This is not an analytic formula, but a very good approximation. And as I mentioned, it's essentially a scalar field. The axion is a scalar field. It's the value. It's associated with the phase of that underlying complex scalar field that got a vacuum expectation value, and it's the most perfect Bose-Einstein condensate ever. If you calculate the amount of energy that's in this background field, it turns out that it's comparable to the dark matter density that that astronomers have discovered. This is a remarkable coincidence and encourages us to think that the axion may be supplying that mysterious dark matter. It has all the right properties. Its interactions are very weak. It's produced in the early universe abundantly. So let me say a few more words about Accion Cosmology, because that's a very interesting subject, a very important subject, and also key to the searches. There are two basic branches of Accion Cosmology, depending on whether, okay, I guess I've lost a slide. Depending on whether the evolution of the universe, once the axion field was formed, is conventional, or whether in between when the axion field was formed and the present, there was an episode of cosmic inflation. There's a lot of evidence now, circumstantial but important, that cosmic inflation did occur in the early universe, So we have to take that second scenario seriously. So in the first scenario, remember there was this initial value of the angle theta, which encoded the value of the Axion field, and that can vary in space. And the correlation length can't be too large because of the Kibble-Zurich mechanism. It can't extend over more than the horizon at that time, which corresponds to a small patch of the sky today. And so if you take a cartoon version of the Axion density when the field first formed, it's all over the place, oscillating between practically zero, where the initial theta, in patches where the initial theta happened to be close to zero, to a maximum value where the initial value happened to be near pi. Or, I guess, yeah, pi. In this scenario, today's universe samples over many horizon sizes in the past when the Axion field formed, and so it's appropriate to average over that initial angle. And if you do that, you get an unambiguous prediction in terms of just f, the one parameter in the theory, for the amount of Axion dark matter there is. And it matches the observed value if f is about 10 to the 12th GeV. Since other observations constrain that f has to be greater than about 10 to the 12th GeV, 10 to the 10th GeV, and remember the Axion density is proportional to f, it is hard to avoid significant Axion dark matter if axions exist at all. And since they're the only way we know to solve this fundamental problem of T violation, the motivation is very strong to take this seriously. In recent work, these estimates have firmed up, and we have a precise prediction for the Axion mass in this scenario, although not everybody in the community agrees with this. It gives us a definite target. The other scenario is if inflation occurs between when the Axion field formed and today. In this case, we still had that picture when the Axion first formed of the different regions of the sky that are causally disconnected, different horizon regions, having independent values of theta. However, the whole present universe arose from a very small patch, so there's only one of these values is sampled in our particular part of the observable universe. So we shouldn't average over theta 0. We have to pick out the value that's appropriate to that particular patch, which we happen to lie in. Then, remembering that the density is proportional to f times sine squared theta, we could have a larger value of f, therefore smaller couplings, and a different phenomenology, as long as it's accompanied by a small value of theta 0. So that might seem unnatural. However, if you consider life in regions with larger values of theta naught, so that the Axion dark matter comes to dominate ordinary matter even more decisively, it turns out that it's very difficult to create observers, practical, intelligent observers in such regions. So anthropic arguments suggest that you should not, you should take the biggest value of theta 0 that's consistent with the existence of observers, and if you try to quantify that, you find out that it's very natural to have the axions being the dominant form of dark matter. So this has some advantages, but many people are uncomfortable with the appeal to anthropic arguments. It's a logical possibility, and in many ways, in some ways attractive. In any case, in either branch of cosmology, so if we take this solution to the fundamental problem of t-violation in physics at face value, it's suggesting the existence of a new kind of particle which almost has to be the dark matter of the universe, and which has definite properties we can look for. And this hasn't failed to attract people's attention. There are many, many experiments that have been done and many, many thousands of papers on this subject. The state of the art is more or less like this. There are lots of values of the parameters of the universe and of the values of f that have been excluded. Those are all those yellow regions. But there are big, robust regions that still haven't been searched and that have been the focus of, that are the focus of activity today. And let me tell you about some of those. So I can't really point very easily. Here, in the triangle in the southeast corner, that corresponds to the post-inflationary, the post-inflationary scenario, the conventional cosmology, and the top corresponds to the actual dark matter density, and the lower parts of the triangle that correspond to axions contributing some but not all the dark matter. On the left-hand side, that big region corresponds to the pre-inflationary scenario. And both are very substantial regions. So people have gone to great lengths and invented many ingenious ideas to try to detect this fundamental target. One is the Axion helioscopes. They attempt to detect axions emitted by the sun. So a large magnet is 5 minutes, okay. Oh boy. A large magnetic field induces conversion of axions into observable photons according to those equations of Axion electrodynamics I showed you. Here's a cartoon version of the experiment. To detect axions that are coming out of the sun, you apply a magnetic field. In the presence of a magnetic field, axions convert into photons, and photons we have various kinds of eyeballs that you can use to look at photons. Here's what it actually looks like in the proposal, and it's actually being mounted, I believe, at CERN. You see this little fellow there? That shows you the scale of this thing. This gigantic telescope, which is meant to point always at the sun, so it has to be movable, contains enormous magnetic fields, and the object of it is to detect axions converting into X-rays that can then be detected. Admx is another mature experiment based on Axion electrodynamics. Here, the same cartoon picture applies of axions in a magnetic field converting into photons, but the nature of the photons is rather different. They are in a cavity, and you exploit resonance to try to build up the signal. I should say the problem in all these experiments is that because the axions are very weakly coupled, which they have to be if they're going to be the dark matter, but also turn out to be theoretically, the couplings are weak, and so you have to work hard to see them, even though they may be providing most of the material mass in the universe. So this is what the Admx experiment actually looks like. You see this one is also large, and this is also cryogenic, superconducting, and lots of fancy technology to get appropriate sensitivity. Admx is another serious experiment using dielectric sheets to get a good match between photons and axions, which start with quite different dispersion relations. So again, to induce resonance, you have to tune things. Casper is another experiment which uses this time-dependent electric dipole moment. But I have very limited time, so I'm just going to zoom through these to show you that people are working hard all over the world, spending lots of money, proposing to spend even more money to detect this really important target that's so central both to fundamental physics and to cosmology. This is the abracadabra experiment, in which you have a magnetic field generated by superconducting coils. A time-dependent axion field in that case will produce currents according to the equations of electrodynamics. And so a time-dependent magnetic field, which you could then detect very sensitively using SQUIDs, superconducting technology. So these are beautiful experiments, but I don't have time to discuss them in detail. Another recent insight is that spinning black holes can lower their energy by radiating things like axions, which then get trapped around the black hole, making a black hole atmosphere. So in this case, this would be a form of hair that black holes could have. And so black holes now have an atmosphere. And this would depopulate some of the space of potential black hole masses and angular momenta, and also affect gravitational wave signals. So as gravitational wave astronomy matures, we'll be able to test this possibility. Okay, now what I wanted to discuss in the second half of my talk is our recent proposal for a new class of axion detectors. I will have to go, however, very, very rapidly and schematically through this. Some of this is repeating what I talked about briefly before, but let me just, so dark matter is an important problem. The strong CP problem, the absence of this potential T violation, is an important. Axions make that dangerous parameter dynamical, so it can evolve, and if you have the right setup, the right symmetry, it wants to evolve to 0. And axions are the quanta of this field that allows the theta parameter to relax. This is the pre-inflationary scenario. This is the post-inflationary scenario. These are the numbers involved in what's possible. So this is another way of presenting the constraint plot, where you can see what things correspond to in terms of that parameter f, in terms of the frequency that's important, that you can convert those masses into. As I mentioned, you have effectively, at the formation of axions, a classical scalar field, or in catchier language, you have a Bose-Einstein condensate. And you can calculate everything about it. We want to convert axions into photons that we can see. One strategy, but the magnetic field gives you a way of bridging them, but even in the presence of a magnetic field, the dispersion relations don't match. One field is massive, the other isn't. So you have to do a little bit more. One way is to insert a space-dependent medium so that you can make the dispersion, change the dispersion relation of the photons and make them match. And that was the basis of Admx and Admx, those strategies. But another way, the new way that we've introduced in recent work that's just about to appear in Physical Review letters, is that axions can mix with plasmons. Another way that photons can acquire an effective mass is in a plasma. Now, plasmas, ordinary plasmas, are really nasty. They're at high temperature and very noisy environments if you were to try to do sensitive experiments. But there's another kind of plasma, which is the plasma of condensed matter physics inside metals. And you can hope to excite plasma resonances at effectively zero temperature in the presence of those kinds of cold free electrons. So a problem if you just tried to use a hunk of metal is that the plasma frequency is much too high for our purposes. However, instead of filling all of space with the metal, you can just fill little bits of it with the metal using wires. It's also possible, and we've discovered probably very advantageous to use superconducting wires. And then you can make a good match between the photons and the Axion dispersion relations. That is, between the massive axion and the massless in free space photons, by making the photons effectively massive, giving them a plasma mass, remaining spatially homogeneous so that the thing can be scaled up much larger than those other designs which relied on putting dielectric plates or other kinds of barriers or whatnot into cavities or just making the cavities small to make the dispersion relations match. So we could make much bigger cavities and get a much more sensitive kind of experiment, we think. And the setup then is very, very simple. You have a background magnetic field, and you have a plasma. Now there's resonance between the photon field and the axion field. The axion field very efficiently pumps energy into the plasmon resonance. And this has many advantages. And here is this plasma haloscope is the thing in green here. And you see it's already with very conservative estimates of the parameters, beating the competition in a significant range, and with less conservative parameters, that we hope that they can really make an enormous impact in this search. Okay, so it has, the big advantage is this first one, that because you're matching at zero without introducing any momentum, without needing to introduce momentum by making a small cavity or putting in a structure, you can make much larger volumes. So, summary and prospects. Axions are a uniquely attractive solution to a deep conceptual issue, why time reversal symmetry is observed to be a very good but not quite precise feature of the fundamental laws of physics. If you take that solution, which is the best and essentially the only one we know, seriously and work out its cosmological implications, you find that the axions, the quanta of this field that solves the problem, must contribute significantly to the dark matter density, if they exist at all. And ingenious ideas and heroic engineering can bring that elusive, weakly interacting dark matter into view. So in coming years, I hope we'll restore the balance between past and future, and at the same time be unveiling what the dark matter is. Thank you.
Thank you very much. Thank you very much. Thank you for a nice talk. I'm here. You cannot see me.
Oh.
Hello.
Hi.
You are talking about properties of axions, and I understand most of those experiments you were talking about are just to demonstrate that axions exist.
Yes.
However, one of the property of axions is their mass.
Yes.
In some of your transparencies, you are rather focusing on low mass axions. However, there are also searches for higher mass axions, for instance, when looking to diphotons.
Looking to what?
Diphotons. Two photons, diphotons.
Oh, yes.
So my question is, what do you think about these larger masses, or do you have a preferred range of masses which should be considered, or you think all these searches for heavy axions are also valuable from your perspective?
Well, I would say the straightforward theories of axions that can be implemented in models that aren't very complicated and solve the problem in QCD are the range of parameters that I've discussed. You can have other things that people have called axions, and nowadays people call all kinds of things axions. That's part of the confusion. Basically, they try to rob the prestige of axions by using the same name for ideas that don't have the same properties of uniqueness or solving the fundamental problem that's given to us by time reversal violation. It's interesting to do experiments that explore for phenomena that might have been overlooked, that wouldn't have been detected in any other kind of experiment. But these searches for higher mass, so-called axions, or for that matter, for lower mass or different coupling strengths, many, many things that appear in the literature, I would say they're interesting to look for, but they shouldn't be called axions, and they're not really, they wouldn't solve the fundamental problem that axions are meant to solve. So I can say good luck to those experiments, but actually I hope they don't find anything. I want the real thing.
Suggest we just have one more question.
Yeah.
Through Netter principle would mean that energy is from itself.
Come again?
Netter principle about symmetries says that the time reversal is essential for the energy conservation.
No. Time translation symmetry is related to energy conservation. Time reversal is quite different. Okay.
Thank you.
By the way, I talked about time translation symmetry last week here in Krakow. There was a whole conference about time crystals, and that's a fascinating subject, but it's a different subject.
Thank you very much again. I think we have to continue.
A short philosophical comment. As time flows or passes, it should be no surprise that there is some time reversal violation on the fundamental level of physical description. On the contrary, I think it is surprising is that such cases are so rare.
Yes, I completely agree, and I hope I got that message across. It's a big puzzle why time reversal, microscopic time reversal symmetry is as good as it is. If it were perfect, we could say, oh, well, it's just perfect. That's the way it is. But it's not perfect, and so we have some important explaining to do. That's what this is all about. Okay, thank you. All right.